if you think about it, anytime your primary activity is calling other people's functions, well, maybe you might use somebody else's decorator, but you're probably not going to write your own decorators and probably not even deal with decorators at all. Anytime your primary activity is to write a function and associated with the writing of that function, you do something in common, that's when you start to see decorators and higher order decorators. Because a decorator or higher order decorator is merely the acknowledgement that Python functions exist at runtime, they are first class functions, and as a consequence, we can do some metaprogramming across them. Well, if our primary activity is not writing functions, we likely will not come across decorators that much in our work. But if our primary activity is writing functions and we need to eliminate update anomalies across the writing of those functions, well, that's exactly when a decorator will come up. Let's talk about metaclasses. When would you actually write a metaclass, and are there better approaches than metaclasses? Let's take a look. Remember that a Python class is how we implement the Python vocabulary. We implement special underscore methods, and those underscore methods allow us to be responsive to aspects of the Python vocabulary like the square bracket syntax or the built-in len function. And so here we have a very simple example of an instance, and you can call len on that instance, or you can use the square brackets on that instance to do something, hopefully something useful. These two implementations of getItem and len aren't particularly useful in practice, or aren't particularly useful in this case, but they're illustrative of what is possible to do. We might implement len if we wanted to express that this object had a non-negative integer size, some concept of a non-negative integer size. We might implement this getItem to represent that this object is some sort of container, has some sort of constituents, and this is our way to, without modalities, look up an unbounded, or look up a constituent of this via some unbounded key. There are other protocols that we might implement, but of course that's going to require us to really think through what code is going to make sense for our end users based off of the intuitions they've developed by making use of common third-party modules like pandas or numpy, or by using things in the Python standard library like the collections module, the chain map being a great example, or by using the built-in types. And if we can write some code that is intuitive based off of people having that background, well, then that's the decision point which leads us towards implementing this vocabulary. When we look up the underscore methods that implement this vocabulary, we don't look them up on the instance, and we don't look them up via the getAttribute protocol. In fact, this is closer to more of a direct C-struct lookup, which is why you can't use getAttr in order to simulate access to, say, underscore len. However, when you think about it, all you're really doing is you're saying, here's some object, what's its type, and then a C-struct lookup into that type, at least in CPython, a C-struct lookup into that type to figure out where is the underscore len, where is the underscore getItem, or similar. Which means if you wanted to implement the same vocabulary, not on an instance, but on the type itself, well, this code here is what happens when we implement getItem or len on an instance. A metaclass is that one level higher. If we ask an instance what its type is, if we ask the object that we have here what is its type, it'll say my type is T. If we ask T what its type is, it'll say my type is T meta. Therefore, if we ask this instance where is the implementation for len and getItem, if they're present, it'll say it's on my type. If we ask T where its implementation of getItem and len are, well, it'll say it's on my type, which happens to be this meta type, this metaclass. In fact, the implementation of the Python vocabulary on types themselves is really the one thing that metaclasses can do these days where you still strictly need them. In other circumstances, as we'll see, there's other approaches that may be superior to the use of a metaclass. Now, there's not a whole lot that we can really do implementing the Python vocabulary on a type. You'll see this is used a little bit in, say, some of the type hinting stuff in order to give yourself some nicer vocabulary for indicating, for example, that something is a dictionary of strings to integers or a none value. But for the most part, we're kind of limited. There's really not that many interesting things that we can do. One interesting thing that you could think about, however, is if that open-close parentheses implements the call protocol on an instance, then the open-close parentheses on a type, which creates an instance of that type, well, it's got to exist somewhere. It's got to be implemented somewhere. Well, Well, it's implemented on the metaclass, which means if you wanted to, you could implement call on the metaclass of some type, and you could completely customize how creation of that thing works. Here, you can see I'm simulating something akin to the dataclasses.data class, where I use new in order to create a new instance of this class. I use init to initialize that instance, and then I even implement the ability to do a post in it, where I'm doing some additional data normalization or data cleanup. Again, we start to get very abstract or very esoteric when we do these kind of things, so it's unlikely that we're going to find really obvious examples where this is going to be useful. And this is also something that is somewhat unfamiliar to typical Python programmers, so it's likely that if we were to do something really crazy here, it might lead to code that people don't really understand. Why are you doing it this way? What's going on? It could lead to a lot of questions. Let's talk about what a metaclass historically was able to solve as a problem. If we think about some relationship between two pieces of code, where some of that code is library code and some of that code is script or application code, where the library is written by one author and the script or application is written by another author, we could think that sometimes the library author needs the application developer to do things in a certain way. Sometimes the application developer needs the library author to do things in a certain way. And there can be constraints moving in both directions. Here, we see an example where the user of this library needs to call a helper function. Therefore, this helper function needs to be implemented by the library author. How does the user of the library here ensure that the author of the library does things in a certain predictable way? Because if the library author removes this function, well, our code will blow up and it'll blow up at runtime. However, the library user in this code can easily check. Take a look at what I'm going to use. I'm going to import base from some library. Take a look at that and tell me if it looks right. The library user can enforce constraints against the library author almost trivially without ever touching the library author's code. They can, prior to deriving from some base type, they can check that that base type has attributes. They can check the signature of those things. They could even just write unit tests that just exercise basic functionality and maybe even implicitly exercise functionality that's available on that base type. In practice, it is almost trivial, and there are a number of different ways for us to enforce constraints from derived types up to base types, from application code up to library code.
Thanks for watching. If you enjoyed this video, give it a like, hit subscribe, and check out the recommended video on the screen. See you in the next one.